Imagine a computer so powerful it could crack today's most secure encryption in seconds, simulate the entire behavior of molecules, and solve complex problems that would take classical machines thousands of years. That's not science fiction anymore. Welcome to the journey of quantum computing, a path that began in theory and is now inching closer to real-world applications. The roots of quantum computing can be traced back to the early 1980s, when physicist Richard Feynman posed a bold question. Why not use quantum mechanics to simulate quantum systems? This seemingly simple idea sparked a revolution. Unlike classical computers, which use bits to process information as zeros or ones, quantum computers use qubits, units that can exist in multiple states at once thanks to the principle of superposition. I end those early days. The concept was more philosophical than practical. It wasn't until the 1990s that breakthroughs like Peter Shor's algorithm, capable of factoring large numbers exponentially faster than any known classical algorithm, proved that quantum computing could outpace traditional machines. This shook the cryptographic world and thrust quantum computing from academic curiosity into technological urgency. Fast forward to today, and tech giants like IBM, Google, and startups such as IonQ and Rigetti are racing to develop viable quantum processors. In 2019, Google claimed to have achieved quantum supremacy with a 54-qubit processor that solved a problem in 200 seconds that would take a supercomputer thousands of years. While the claim remains debated, it marked a milestone in making quantum theory a practical pursuit. What makes quantum computing especially thrilling is its potential to revolutionize everything, from drug discovery and climate modeling to financial forecasting and artificial intelligence. Yet, building a fully functional, error-corrected quantum computer remains one of the greatest engineering challenges of our time. Issues like qubit stability and quantum decoherence still limit current machines to highly controlled lab environments, but progress is happening rapidly. Hybrid approaches, like quantum classical computing, are already being tested in real-world scenarios. Quantum cloud platforms are now accessible to developers and researchers, opening doors to innovation once restricted to elite labs. So, is quantum computing the next big leap, or just a beautiful theory still decades away from practical use? As with all great technological shifts, the answer may lie in how we embrace the present and imagine the future. What part of quantum computing excites you the most? And how do you see it changing our world?